Thank you. So, like Igor Aronson's talk yesterday, mine is going to be on biofluid mechanics problems, very similar, if not identical, set of issues. And so you heard some of that from him yesterday. Oh, sorry. The man waving to me in the background says, turn on my mic. There we go. Okay, and as you will rapidly see, my background is more in computational fluid dynamics rather than in analysis, so I won't be giving theorems and compensated compactness arguments and so forth. So, but my interest generally in fluid mechanics has to do with fluid-body interactions, and so those of you that know me might be familiar with some of my work on the flapping of flags and streamlining of elastic bodies and so forth. And another set of systems, which are kind of extreme versions of fluid-body interactions, are complex fluids. And so complex fluids are, as many of you know, fluids that have suspended microstructure, that have various types of mechanical responses, or in the cases that I'll be talking about today, actually can pump energy into the fluid because they are, say, converting chemical energy into locomotion. And so what I'll mostly be talking about today is this problem, which has to do with the emergence of large-scale mixing flows in motile suspensions. So these are suspensions that are made up of, say, many locomoting bacteria. And so Igor introduced that to you yesterday. But there's lots of other very interesting problems that involve complex fluids in biology. And so I and my collaborators, for example, have worked on motility of undulating organisms, say a spermatozoa, through a complex fluid, say, which would be a model for cervical mucus. And more recently, with one of my postdocs, Tamar Shinar, we've been working on problems in developmental biology that have to do with the interaction of microtubules that are growing from a nucleus in a single-cell embryo of C. elegans, as that this is a microtubule, just a stiff polymer that's grown out into the cytoplasm, and the cytoplasm is filled with motor proteins that clamp onto it and can exert stresses and move things around. So we've been examining that class of problems. I doubt I'll have the time to go into that at all. So, but here are some experimental pictures of various of this kind of set of problems. And so I'll be talking about this problem today in some detail. And there's a sperm swimming through a synthetic viscoelastic fluid. Actually, it came from a group at Oxford, and we found their data very useful. And here's a few frames from a movie from my experimental collaborator Fabio Piano's lab at New York University, showing the male pronucleus growing these filaments into the fluid, which are GFP labeled, and so you can fluoresce them and they show themselves to you, and it's pulling itself towards the female half, and they're meeting, and various types of things having to do with cell division then take place. But this is the problem I'm going to be talking about today, which are the dynamic of active suspensions. And so active suspensions, very broadly, are those where the microstructure can dynamically change its shape. And so, say, it might just be a flexing rod, or it might be exerting a propulsive stress on the fluid and then moving itself around and pushing on other such elements. And this is the bacterial bath example. And this came from John Kessler and Ray Goldstein's lab then at Arizona, and now Ray has moved right next door here in Dampt. And so what this is showing is the roiling dynamics of a bacterial bath made up of Bacteria subtilis, which is just a kind of rod-like bacteria that has a long flagellar bundle at the back. And it turns that flagellar bundle and it swims around, and here's many of them in suspension, highly concentrated suspension. And so what you see is that there's a lot of very complicated spatial and temporal structure in this dynamics. And as Igor talked about yesterday, it's been postulated and will provide, I think, a lot of theoretical proof for that statement, that a lot of this dynamics is mediated by the fact that they're suspended in a fluid, and that fluid allows them to push on each other through the fluid, and so have a big coupled n-body problem in the context of the Stokes equations, if you like. And so what these experiments have shown is that there are correlated space and time scales that are much larger or longer than those associated with any single bacterium. there seem to be large-scale density fluctuations, suggesting some sort of self-organization may be going on, some concentration effects. There's lots of very interesting, there's diffusive behavior, I'll talk a bit about that. And so there's lots of interesting questions that arise in this. And for example, how does the method by, now see, I'm going to work with a model of swimming rods, so I automatically take this, I hold this in my hands, and I expect you to look at it as my mathematical model, which I will in just a second. But one question is, if I have a swimmer, there's various types of swimmers. And so, for example, there's a sperm which is pushing waves down its tail. If you like, that's something that is being propelled from the rear, so-called pusher. There's an algae, Chlamydomonas, which is pulling itself forward by flagella in kind of a breaststroke. Those are called pullers. Hopefully I said pushers and pullers. Paramecia, which is just covered, a ciliated organism, which is just covered by little breaststroke cilia that are moving it around. Those somewhere sit between these two worlds. C. elegans, for example, which is a swimming worm that just puts undulations down its body plan and moves itself around. And so interesting questions are, if you're looking at the coupling between microscopic dynamics and macroscopic consequences in terms of large-scale flow, how do these kinds of details actually influence what happens? And it turns out that there's a very interesting story in that. So, and that will be roughly in that last sentence, a lot of what I'm concerned about is what is the coupling between microscopic swimming dynamics, immersed in a fluid and hence pushing on other swimming particles, and that of the large-scale flow that may or may not erupt from that. So here's our basic model that I'm going to concentrate on. And both at the level of posing a interesting kinetic theory as well as looking at many swimmer kind of point simulations and body simulations and comparing the two of them. And so, and this is work with David Santillan, who had been a postdoc of mine at Courant a few years ago. He's now at Illinois. And so a lot of the work will be joint with him, but our basic model is founded on slender body theory for the Stokes equations. And so what we will be considering, because it's rather easier computationally, is to be considering a suspension of swimming rods, okay? And so here's my rod. We use slender body theory. That's quite slender. It looks like it's about an aspect ratio of 1 to 30 or 50, something like that. And so the way these rods are going to get around is, say, this guy's swimming in that direction. And so what we will posit is that there's a propulsive stress on the posterior of the rod pointing backwards. So we're going to impose a shear stress on the boundary. So we're going to prescribe it. And so this is some sort of coarse-grained model, say, for the flagellar bundle pushing fluid back, and then you can interpret that as some sort of stress on the boundary that's pushing fluid back along its axis. And then along the front, we'll apply a no-slip condition, and that's the cargo. That's the cell body, for example. And so that separation actually between a propulsive area of the swimmer versus that is the cargo and has a no-slip condition is very important in understanding a lot of the large-scale flow effects, as a matter of fact. And you start to see it right here. So here for a swimming rod, swimming upwards, this is a pusher. And so you can see that fluid, there's the flow field around it, and you can see the fluid is being pushed down along the posterior. It has a no-slip on the front, so it's moving up and it's dragging fluid with it. So in the lab frame then, there's a velocity field up along the body. And so what you see then is that by that, putting the motive stress at the back, and the no-slip at the front, is that you create something like a straining flow, an extensive straining flow around this swimming object. That's its local flow. Here's a puller, and a puller now is fluxing fluid back along the front. It's still moving upwards, and it's dragging the rear. Oh, I'm sorry, this is yeah, that's extensive. Good, I said that correctly. And then you end up having, again, a extensional flow now, which is compressive along the rod. So the main thing that you see right here is that the local flows by which they may be interacting they're moving in the same direction, but they have different signs. So you can already see, kind of in a simple way, that they're going to have different interactions with each other if I'm a suspension of pushers or a suspension of pullers. Now both of these have velocity fields that decay like 1 over r squared. Now, there's something that's more like a ciliated organism where you're just going to cover the whole object with stress. And then it turns out that so I should say that these decay like 1 over r squared because, as Igor intimated to you yesterday, the far field flow is that induced by a force dipole. And here, if you have this kind of symmetric arrangement where you have no cargo part, then it turns out that force dipole is small or 0. And so you pick up an extra order of decay. Tim Pedley called this a stealth swimmer. They tend not to interact with each other very well, so we're going to ignore them altogether. Too stealthy for us. Okay, so the first thing that David and I did a few years ago, in fact, David did by using a lot of computational fluid dynamics machinery that he had developed in his thesis at Stanford in looking at settling rod suspensions, was to adapt that settling rod suspension code to that of these kind of motive rods. And here's one of the first simulations that we did, and this is from a PRL in 07. So, now where's my pointer? This is rather disturbing. Fortunately, this is a tablet, so I can access this through other means. There we are. So, this is a simulation where we start off with a suspension of about 2,500 rods, all pointing in the same direction in a 3-dimensional volume. And so what we were interested in looking at was whether you would see something like flocking or kind of organized packs of oriented rods swimming around. And what we discovered very rapidly is that there was an instability, kind of on the system scale, that destroyed the orientational order, and that this flow, now you have to understand that each of these rods left by itself would just be locomoting along its axis at a constant speed. But now they're all pushing at each other through the fluid that separates them, and it has created a large-scale flow. That's something you should be pulling out of this just by looking at it. And it turns out that this flow had many of the characteristics that were seen in these original experiments out of the Kessler-Goldstein group. For example, the velocity fields that were underlying the propagation of all of these rods around tended to be correlated on the system size. It would have vortices and jets and so forth. It was highly dynamic in time, and so on. So that was our first take on that. Now, it turned out to be difficult to get any sort of analytical insight into the dynamics of these suspensions in what is essentially just a big piece of code. And so instead what we decided to do was to develop a kind of a suspension theory for this, and I'll kind of detail this for you a bit, just walk you through a couple of steps on how these go. This is basically the kind of ansatz of Doy's rod theory, for example, for passive rod suspensions, if you read chapter 9 of Doy and Edwards. So here's our very simple swimming rod. And so here's a pusher. It's got motive stress along its tail right here. I put that in black. And it's moving forward. This is the no-slip payload, so to speak. And fluid mechanically, it's of course exerting a stress on the fluid. And in slender body theory, which we will be using, instead you deal with a force per unit length, which is this force F right there. And because you have to accommodate, you've said that there's an imposed tangential stress, you have to then accommodate into this model a slip surface. You have to allow the fluid to slip along it there. And so there's my rod. I've just written it out in terms of the arc length and a director vector, which is telling you what direction its axis points. And I have a small aspect ratio, epsilon, r over L, the radius of the rod over its length. And then there's a very classic result, local slender body theory, which is what I'll use for this explanation, which governs the dynamics of a slender rod and in a Stokesian fluid. And so then it just says that the drag force is balanced by basically the motive forces and the forces of constraint that say it's a rigid rod. And the main thing here, the only thing that survives of the Stokes equations, oddly enough, is that in local slender body theory is just a tensor that tells you that it's, if you have a given force, you'll go twice as fast along your axis for that force if it's pointing along the axis than if you were going orthogonal to the axis. So you have this little anisotropic drag tensor sitting right here. So there it is. So if I know my forces and I know my background flow that this is moving around in, then I can calculate the velocity along the center line of this rod. Okay, so if we're looking at a pusher then on the anterior, the back half, we're saying that the force is some applied force given along the axis plus some piece that we need to determine, and that the velocity along the surface looks like the motion of the center of mass, the piece that comes from the rotation of the director, as well as some slip surface, or rather slip velocity on the surface that I have to allow since I've then specified a part of the stress. And likewise on, I always get posterior and anterior mixed up. Anyway, on the front part, I think, then this is where I have the no slip condition. And so it just says the surface velocity is just that's associated with the translation and solid body rotation of the rod. That's it. Now, if you're dealing with a free object with no body forces acting on the system in a Stokesian fluid, or have an overdamped system in general described by a stress tensor, then what you have then, you have the constraints on that object that it can exert zero total force or total torque on the surrounding fluid. So everything in the low Reynolds number, if we take the limit of zero Reynolds number world, gets around under the condition that it can't exert a net force or torque. And that's why you see the types of locomoting, well, okay, let me not go off into that. But anyway, that's a condition. Okay, so if I take that ansatz, then I can calculate what is the motion of this simple rod. And what I find is that the motion of the center of mass is given by and what I've done is I've assumed that the rod is much smaller than the length scale associated with changes in the velocity field. So I've done a linearization. And so then I have that the motion of the center of mass is just that of the local flow, the background flow, plus just the propulsive part inducing some velocity u naught. And that u naught can be expressed in terms of things with this surface stress being given along one part of the rod. The viscosity, the length, the surface stress, and a geometric coefficient kappa 2. Then the rotation is given by the classic Jeffreys equation for just a slender rod in a background linear flow. And so it just says, you know, I have my gradient of the velocity field, I have my director, and it will rotate the director, but since it's a director and it has unit length, then I have to project off the changes in length, and that's where that guy shows up. Okay. Now, so if you like, in a kinetic theory, these are the single particle fluxes right there. Right? There they are. So my configuration variables are going to be x, the center of mass, and it's going to be the direction of the swimmer in my kinetic theory. Now, what I need, though, is I need to know, having gotten the fluxes, I need to know how to reconstruct the velocity and the gradient of the velocity. And so that comes from a classic Kirkwood formula, or if you like, Batchelor 1970, that tells you how to calculate that for a set of objects suspended in the fluid. And so I have that are exerting a stress, and so you can calculate the volume average extra stress, which I'm going to use then to drive the fluid, for having n suspended rods. And you end up with the following, and there it is. It's just a formula. So it's this rank 1 tensor sitting right here, a sum of them. So it's the body position times, and this is for force-free particles, it's the body position times the transpose of this force unit length along the rod. And then you can calculate for a single element in this ensemble of rods, you can calculate what its contribution to the stress is. And it turns out to have two pieces. One that just comes from the stress that's induced by it moving itself through the fluid. Okay, just a single isolated rod. And there's another geometric coefficient that depends on its shape that pops in. There's the surface stress. It's got an L cubed. L is the size of the rod. And then there's a piece that comes from the presence of background flows that are inducing forces that are associated with constraints of having to remain of constant length and being rigid and straight. And it turns out that in the problems I'm interested in, you can argue that this will be a higher order effect, because we're not going to have a background flow. They'll develop, and they'll be proportional to volume concentration. So it turns out you can argue this is a smaller order effect. And so I'll just take this leading order term right there. And so then if I have a set, now the thing that's interesting here, I should say, is this sigma naught, this size of the stress, if you like, stresslet strength. So if I have pushers, then it turns out that sigma naught is negative, and if I have pullers, sigma naught is positive. And that corresponds exactly to those changes in the sign of these straining flows in the neighborhood of the body. So the stresses that are being exerted on the fluid change according to whether you're a pusher or a puller, the sign of the stresses. Now this is actually the same kind of effect that Igor was talking about yesterday when he was talking about, well, if you have pushers or pullers, does it have, one will have an effect of lowering the viscosity, bulk viscosity of a fluid, while pullers may be raising the bulk viscosity. So you see it again showing up here. So the way in which microscopically these little guys get around matter very much when you're generating large-scale macroscopic stresses. And so then what I'm going to do is I'm going to replace these with distributional averages. I'll introduce a distribution function and a Fokker-Planck equation for the evolution of the distribution, where now again my configuration variables are going to be x and p. So there it is. And so this was a couple of more papers with David. There's my continuity equation for a distribution function. And there's some normalization, which is not so important. And then I have these particle fluxes, which I just calculated on the previous page. And then I have to close this dynamics by saying, well, how do I get my hands on U and how do I get my hands on grad U? And so what I do then is I solve the Stokes equations for the background kind of solvent velocity or macroscopic coarse grain velocity under the presence of these various active particle stresses, which I just calculated on the previous slide. So there's my momentum balance equation then. I just have the Stokes equations, which will give me the velocity of the background flow. And then it's being forced by the divergence of that active particle stress. And there's the active particle stress now expressed in terms of a distributional average rather than this sum sitting there. And again, pushers have this sigma naught being negative while pullers have it being positive. Okay. Now, if you non-dimensionalize, it turns out that there's an whole interesting story with the non-dimensionalization, which I won't refer to too much, except to say that you can eliminate all but two parameters in this problem, and in this set of equations. One of which is the sigma naught can be, under appropriate non-dimensionalization, replaced by alpha, which is an order 1 coefficient, which is a ratio of these two geometric parameters I was telling you about, plus a sign according to whether it's a pusher or a puller. And the other, and that involved actually calculating an intrinsic or characteristic length of the system, which was the length of a single swimmer divided by the effective volume fraction that they take up in the fluid. So effective volume fraction is simply take their number. Each rod has a length L, and if you spin it around, it maps out the volume, right, of a sphere. Just take n times that volume, divide by the total volume of the system. That's the effective volume fraction. So it's that n, so n is a number density, and then times this little L over 2 cubed. And then it turns out that the other parameter is just the ratio of the system size divided by this intrinsic length. So there's only two parameters in the problem as I've given it so far. Well, I lied to you a little bit. There were some diffusive fluxes on the previous slide for a rotational and a translational diffusion, which has a couple more parameters in it as well. So, okay. So it turns out that this has a configurational entropy, which is very interesting. There's the usual object. And so psi naught is just the entropy associated with being in the uniform isotropic state, which is, in my scaling of the system, 1 over 4 pi. And when you calculate the derivative of the configurational entropy, you have the usual kind of diffusive pieces that are associated with the rotational and translational diffusion of these particles, driving down the entropy, while there's this other term, which is basically the rate of input power, or it's the input power term, let me put it that way. And it comes with this alpha floating in it. And if I go back to the momentum equations, then I can calculate what this is and express it in terms of the rate of viscous dissipation. And so then what you see is that the entropy has one term which is decreasing it, but it has another one whose sign, which is proportional to the rate of viscous dissipation. It has a term whose sign depends on whether it's a system, whether it's pullers or pushers. And so actually the entropy will not decrease as it would for just a passive rod suspension. For a passive rod suspension, it turns out that this alpha is positive, as though you had a set of pullers. But for pushers, you change the sign, and now you have a term that can actually drive up fluctuations by pumping power into the fluid. Fluctuations is measured by this entropy. So then you have that for pullers, then fluctuations as measured by S will dissipate, and you'll tend to go down to the uniform isotropic state. Well, for pushers, input power from the swimming can increase fluctuations until that increase is limited by diffusive processes. Okay, so now, I do various types of stability analyses on this system, including on the slides which I have hidden from your view that have to do with the stability of oriented suspensions. So we can do a calculation on the stability of oriented suspensions and show that they're always unstable. But what's actually more interesting, once you know that oriented suspensions are not of interest, the thing that's really interesting, also because you have this entropy equality, is what is the stability of isotropic suspensions, which is kind of the natural reference state that we're dealing with. And so, so then if you look at the stability for just a bunch of swimmers, going willy-nilly, kind of with uniform probability in any direction and with uniform concentration, and you linearize just around that state with a spatial Fourier transform, you can derive a relation from the equations of motion, kind of an integral equation, for the eigenfunction, which still depends on the orientation vector on the sphere. And so, and this F is a following integral operator. This is your normalized wave vector, and there's some integral over the sphere of the wave vector dotted with the orientation vector, and so on and so on. But at any rate, there's the equation. And if you apply F to both sides of this equation, you can derive an eigenvalue relation, and you can look at growth rates and so forth. Now, this is a problem for which you don't have any, because it's variable coefficient in P, you don't have a guarantee actually that the eigenvalue problem exists in its solution at all. But so you make it as an ansatz and you find that it does, at least for a range of values of K, it turns out. But here's what you find. What you find, so now this is the growth rate of perturbations from being in uniform isotropy. What you find is that for pushers, you have, as a function of the modulus of the spatial wave number, so this is giving me an inverse length scale, you have that at large length scales, there's two branches of instability, with one reaching a finite value as K goes to 0. Then as you increase the wave number, and actually this is neglecting diffusions in this particular case, and then it merges into a single branch which comes down, and when it hits the axis, you see the emergence of two oscillatory modes coming out in the fluctuating part of the perturbation. And so if you have a suspension of polars, it turns out you just flip this whole thing down and you just have two stable branches. Now there's a whole question about what happens when you hit the axis here. It turns out that you can actually show that once the growth rate, if you lack diffusion, hits the axis, you don't have a solution on the other side. You lose existence of solutions to the eigenvalue problem. And so you have to go to other means actually to understand stability. And that was actually work that I did with another of my postdocs, Crystal Hohenegger, in which we use kind of a Laplace transform argument to talk about what happens to the dynamic equation, which is given here when you're looking at high wave numbers anyway. And we could show that actually it was well controlled. You didn't have any sort of stability problems, no well-posedness problems at high wave numbers. Okay, but there was something more interesting actually that comes out of basically the scaling of the problem. So what I didn't tell you is that one of the things that David and I discovered when you're looking at the dynamics of these rods as a big numerical code is that at kind of in the range of going dilute to semi-dilute. Semi-dilute means that effective volume fraction approaches 1. Okay, and so effectively all these spheres that are containing all these little rods, they start to fill up the whole volume. Okay, and so up to that point, what we found when we measured the rotational and translational diffusion, we discovered that the rotational diffusion scaled linearly with volume fraction, which makes sense if the rotation of a swimmer is mediated by kind of episodic interactions with other swimmers. And hence, you can have something like a generalized Taylor dispersion, which Brenner analyzed, that would tell you that your translational diffusion is enslaved to the process of the rotational diffusion, because you just have this, something like a random walker. He's moving along, he gets deflected, moves along, deflected, and so then the rotational diffusion tells you what your translational diffusion is going to be, and we found that and so hence the translational diffusion scales inversely with volume concentration. Now, it turns out that in that regime, what Crystal and I were able to show is that you get a very nice stability threshold that pops out of that, because it still turns out you can rescale the whole system so the volume fraction disappears out of the rotational translational diffusion, disappears in other places, and only shows up in this intrinsic length scale that we use to rescale the system size. And then in that case, what we discovered is that we had this nice stability criterion where the effective volume fraction times the ratio of the system size to the swimmer length, if that exceeded a number which depended on this dimensionless coefficient alpha, the size of the dimensionless stress, then you would see the emergence of large-scale flows. You would become unstable to large-scale system size, perhaps, perturbations. And so then we calculated that for those rod calculations of ours, Crystal and I calculated that if I fixed this ratio to be that in accordance with our simulations, then we calculated that this new tilde effective volume fraction, which we would see a stability transition, be about 0.9. And so David and I decided to go back and look at that because we hadn't looked at it very cleanly. But let me show you, before I go back to the rod simulations and start comparing with the predictions of the kinetic theory, what I wanted to do is just show you some of the dynamics that one sees directly out of the kinetic theory itself. Okay. And so David has since done 3D simulations, but let me show you some older 2D simulations. Now 3D is kind of tough because actually you have 5 plus 1, you have 5 spatial variables plus time, because you're seeing on the unit sphere plus 3 dimensions for your center of mass. But on the other hand, if you're in 2D, then your orientation just sits on the circle and you're just dealing with 3 degrees of freedom. And so that's just a nice 3D numerical simulation, which we can do. And so what I'm showing you here are some simulations of the kinetic theory where we're starting off with having, I think, somewhere on the order of 5 or 6 unstable modes in the box, according to the way we've chosen parameters. And we're starting off with something that is near isotropy plus a bunch of small modes that we've added to it. Okay? And what you're seeing here is the mean director field, the mean swimming direction coming out of the kinetic theory. And you start this off. If I can, there we go. Oops, wasn't firm enough. There we go. Now what happens, this is the concentration field, is that those high frequency concentration fluctuations decay away. The whole system kind of relaxes. But then you'll notice that actually the director field has smoothed itself out in acquired dynamics, and then you start to see concentration fluctuations sitting on the left there. And then it has an extremely interesting behavior. What happens is that you see kind of bands of concentration which become transversely unstable. They fold, and then you end up getting a band in the orthogonal direction, and just this process just repeats itself quasi-periodically in time. So it's very dynamic, but it also has somehow a very simple underlying system that's sitting in it that we haven't gotten our hands onto, which has to do with formation of concentration bands and transverse instability. So what does that sound like? Well, that sounds like stretch and fold, actually, right? So you would anticipate that you have a stretch-fold dynamics in this system, and it actually should be pretty good at mixing fluid as a consequence. So, but here's some of the Fourier modes evolving in time. One thing I didn't tell you, which is interesting, about the results of the linear theory, is that the eigenmodes of the linear theory do not predict that you, and this comes from the more general dynamic linearized equation as well, not just the eigenvalue problem, but what it predicts is that your instability is not associated with concentration fluctuations. You're not becoming unstable because you're getting clumps of swimmers getting together and then the concentration is growing. Turns out that's not the case. What actually causes it is that you start to get orientation of the director field. And it's modes of having oriented director fields that actually drive the instability. And so what you typically see in these simulations actually is that first you see the rise of fluctuations in the orientation field, and then nonlinearly over time, that drives concentration fluctuations. So whatever these states are of stretch and fold, we're not going to describe them by kind of basically some analogy with the linear problem. It's quite different. Okay, anyway, that's, in those words, that's what this was all revealing to you, except to see that these spatial Fourier modes plotted in time are moving up and down in some sort of quasi-periodic fashion. Now let's take a look at the entropy. And so here we're starting off with nearly zero entropy. We're right near the isotropic state. And so then you can see that, and this is actually just the input power, the active particle power, which is its integral over space, then gives you the, well, just concentrate on this. This is the total entropy. So I have a little misprint over here, so now I don't want to talk about it. But if you take a look at the total entropy, it starts off near zero. You can see those high modes decay away, so these are for pushers. So it decays away, it gets even closer to zero, and then concentration fluctuations start to develop. And then at some point, it grows and saturates, and then you get this quasi-periodic behavior where you're being limited by diffusion. On the other hand, polars, just as predicted as you knew, because you actually just had essentially a theorem by deriving the entropy equality, the polars just drop like a stone and the thing just decays monotonically to the isotropic case. Okay. Now, let me show you a movie of mixing. So take the velocity field that's generated by all these swimmers and let it push around a scalar field, which we've colored here. Okay? So before, you were seeing the concentration field, which is there's no sort of invariance associated with value in that case. And so this is just a scalar field being pushed around by the velocity field of all these swimmers. And there we go. So it likes to mix. And it does it quite nicely. Of course, this is periodic boundary conditions, and if you had a system where you had solid walls and so forth, maybe things would be modified if the system were not large enough. But at any rate, this has a nice stretch fold mixing, creates lots of folds, lets molecular diffusion act rapidly at some point, so on and so forth. So they're kind of intrinsically generated mixing flows. And so this is very interesting if you're actually thinking about applications, right? If you're an engineer working in microfluidics, you might like to have a system that has a bunch of pushers pushing around and mixing the fluid kind of nice and isotropically for you. And I should say that there's been a lot of work in the past 10 years or so, actually really the past 5 years, at coming up with methods for having synthetic swimmers that are kind of independent and motile, and some of them are based on kind of using surface chemistry to create kind of something that looks like a local Marangoni stress on a swimmer, and it pushes it around. But there's a lot of work on trying to figure out how to do this in a synthetic system. Of course, mine is wholly synthetic. It's even out of the world, right? It's virtual. So, okay, so what David and I have done is we're now going back and doing a more complete study to try to see whether we see some of these predictions, at least qualitatively, in our rod suspensions. And so what I'm going to show you here is I'm going to have a fixed box of 10 by 10 by 10. Each of the rods is of length 1. And so we're going to start off with small effective volume concentration, which means, according to my theory, that prediction of having this sharp stability boundary from the kinetic theory, that if I'm sufficiently small in effective volume concentration, the isotropic state should be stable. And then we're going to increase it systematically, so from 0.1 to 0.5 up to 1. And then I'm going to show you a simulation at high volume concentration of polars, which my theory predicts should stay in the isotropic state. Oh, come on. There we go. Okay, there's low volume concentration. They're swimming around. Who knows, right? You need to do some diagnostics, but there doesn't appear to be any sort of large-scale flow that's coming out of this. If you look closely, you can see they're kind of bouncing around, changing their orientation as they interact with each other. Now, if I go up to 0.5, well, maybe you start to see some clumping. Maybe it's just random, random clumps. We'll look at that. And then I go up to 1. There we go. I don't know if you can see that well in the back of the room. I can't see anything in the back of the room. But I'll tell you what you're supposed to see, as any good newspaperman would. What you see are you get these large clumps of swimmers that are transitory in their structure. They have members leaving and coming in. But you see these large clumps that tend to be aligned and move quickly. And so they're all kind of interacting and rolling around with each other. But there's something that's organized now in this. Now, compare this with the high volume concentration of pullers, and it's really much different, right? It's just staying isotropic. These guys have interactions all over the place, but it really just wants to stay in an isotropic suspension. Now, on the other hand, you would guess that if I could push in our simulations the volume concentration even higher, then at some point there's going to be some sort of sterically mediated, something like a pneumatic transition. So we're not near that. So they're not too constrained by some sort of wanting to be aligned, but it's really staying in an isotropic state. And we see that in all sorts of diagnostics. And so here's the a characteristic disturbance velocity field from these 4 simulations. And so here's the pushers, pushers, pushers. And so you can start to see that at the high volume concentration, you see correlated velocity fields that are on the box size. So here's some sort of jet. There's something like a stagnation point. There's another jet. Maybe there's a vortex right there. But they're large. Okay? And you see them start to emerge at 0.5, and then you see no sign of them really here for the low volume concentration of pushers, which looks amazingly like that for pullers. Okay? Which is not showing any of this large-scale structure. If you calculate a correlation length of velocity fields as a function of volume concentration, then you see that for pullers, actually you get a decrease in it's basically just on the swimmer length scale. That's the only correlation length that you see out of this. But on the other hand, the background velocity for pushers, as I increase volume concentration, rises and approaches the system scale. It's about half the system size right there at nu equal to 1. You can look at the scaling of these kind of packs of rods that you see swimming around. Okay, and you can compare that with kind of the random packs that you would form just by throwing things down uniformly with a random orientation in the volume. And so in that case, if I have a volume in which I expect for a uniform distribution to have an expected value of n for the number of rods in there, then the random case is governed by a Poisson law, and we can compare our simulations to the Poisson law as a function of n. And so what you find is actually it has tails, so you tend to see packs that have more areas which have more of these rods in the volume than you expect it to have on just the basis of considering it just a uniform isotropic suspension. While it fits quite nicely to a Poisson law, again, for pullers. And you can calculate how, basically, if you're looking at the standard deviation of those distributions, you can search for some sort of behavior like mean of n to the alpha as far as the scaling of the standard deviation. And the Poisson law predicts that alpha should be 1/2. There's a calculation of Simha and Ramaswamy through kind of a phenomenological kinetic theory where they have an argument that it should be 5/6. And we see, indeed, there's alpha greater than 1/2 and somewhere around 0.6, somewhat less than Simha and Ramaswamy, but greater than that associated with a purely random distribution. So it has what is called in the game giant number fluctuations. I like that phrase. So you can look at mean particle velocities of the suspension. And what you find is that the overall kind of velocity of the suspension is increased in pushers as you increase the volume concentration, while it stays really flat and just has the swimmer value because it stays in the isotropic state for pullers. And then you start to see some nice bifurcation phenomena. And so this is looking at mean swimming velocity as a function of volume concentration. It starts to increase, and then maybe being generous with ourselves, somewhere around 0.5, there seems to be a bifurcation, and you start to get much more rapid growth of velocity from being just the single particle one. We also find that the maximum velocities tend to be 3 to 5 times higher than that associated with single swimmer velocities. And actually, again, that's consistent with the experiments of Kessler and Goldstein, Dombrowski, and others. And what we find is that these high particle velocities correlate with two things. They correlate with having a high local density of swimmers in a polar fashion. That's the second point. They tend to be swimming in the same direction. So not only are they aligned, they're aligned in a polar sense. And so there are indeed kind of packs of rods swimming around as a group and gaining a greater velocity through some sort of cooperative hydrodynamic effect. Now, let me show you this same type of simulation again. And so we estimate that somewhere around 0.5, being generous, we see this bifurcation. And it's kind of order 1. It's not so far, 0.9 from that comes out of the kinetic theory. So we're more or less happy. We also find, which I'm not showing you here, that if you fix the volume concentration and you increase the system size, then we also see this crossover again, as again predicted by that threshold criterion that I showed you. So it's all consistent. Now, let me just show you what mixing looks like in this system. So now I'll start off with low volume concentration of pushers. I don't know if you can see this because the room is a little bright. But this is showing, again, just a dye field. And if you're up here with me, you can see it becoming kind of fuzzy. But the way in which it's becoming fuzzy is that you see these little streaks moving through it, which is the effect of individual swimmers passing through the dye and dragging the dye along with it. Okay? And so this has a very slow diffusion that's associated just with the advection of bits of dye with the individual swimmers, not associated with having sort of large-scale flow. Okay, and so you can see it start to fuzz out very slowly in time. And if I take a look at high concentration of pullers, which should also be stable in the isotropic state, you see the same effect, but just faster. And so there's 10,000 swimmers moving around in a volume, and they're dragging fluid and smearing out this concentration field over time. Now I just want you to, now the main thing to notice is that because of the isotropy of this system, you retain the overall kind of sinusoidal structure of this dye field, this kind of blue stripe and this red stripe. But on the other hand, if I take a look at pushers at high volume concentration, then it's a completely different problem. So you have large-scale flows, you have several modes, you have jets, you have this stretch fold dynamics presumably going on in it, and it just mixes the fluid together very, very nicely. So once you're past that transition, then you have a nice mixing fluid. So we measure that with what's called a multi-scale mixing norm, which basically measures the number of folds that are sitting in a scalar field, roughly. And so just an h to the minus a half norm on some concentration field. And as it halves in size, you're basically doubling the number of folds that are sitting in the fluid. That's what it's measuring. And so then you can see that for pushers, as I change the volume concentration, that one going down rapidly is going down exponentially. That's nu equal to 1. And it goes down yet more and more rapidly as I increase nu. On the other hand, for pullers, it stays more or less flat, showing a slow decrement that increases linearly, whose speed of decrease or rate of decrease goes linearly with volume concentration. And then here is what we call the mixing efficiency, which is just basically the rate of decrement, the exponential rate of decrement, sitting there in W, this multi-scale mixing norm. And so what you see is that you're very slowly mixing if you're pullers or pushers at low volume concentration. Then around a half, it bifurcates and large-scale flows develop, and it mixes much more quickly. You can also look at tracer diffusion and see very similar effects. The tracers will diffuse very slowly in these kind of isotropic cases. They do diffuse because tracer field's being dragged around by the fluid particles. But then around 0.5 again, you see where at the onset of collective dynamics in this motile suspension, you get large-scale flows, and then you will diffuse tracers much more rapidly. So that's just looking at tracer diffusivity. And I think it's a good time to stop. I could tell you about pronuclear migration, but that's another half hour. So there's a lot of things that we're working on these days in my group and in other groups like Igor's. What are the effects of confinement and complex geometry? There's a very interesting study that's come out of a couple of groups, Kenny Breuer as well as Andrei Sokolov working with Igor, in taking bacterial suspensions and showing that you can make it turn a gear in a fluid. You just kind of throw a gear in there and the flow will organize and will start to turn the gear. And so there's a question about, in these active fluids, can you use them to extract useful work? It turns out the work efficiency is extremely low, but anyway, it's fun. And so we're looking at that in the context of this kinetic theory, whether we can kind of embed the kinetic theory in a complex geometry that has some degree of freedom in the motion of boundaries and show that you get something interesting out of that. Coupling to other fields. So there's a big industry these days in trying to build magnetically driven microswimmers. So the simplest case being you just have some sort of helical object that you can exert a magnetic torque on, and then if you can turn it around its helical axis, you can make it swim. It will just corkscrew its way through the fluid. But if it's carrying a payload, it may look like a pusher or a puller. It may have kind of large-scale instabilities associated with a bunch of them, and so that's another thing that we're looking at, is the coupling of the hydrodynamics, large-scale hydrodynamics, to being driven by fields such as magnetic or electric fields. Chemotactic coupling. Microorganisms dump stuff into the fluid, they respond to it, they will seek out oxygen, they will try to get away from things they don't like, and so that's a interesting thing, and so on and so on and so on. And thank you for your attention.